All right, so for this question, it's purely really a calculation question, so you should not really expect a question just like this on the Physics 2 test, but it's good practice sort of reviewing all these relationships between potential, field, current, magnetic forces, induced currents, all of these things. So it's good practice, but remember that in the AP2 test, you're more likely to see, say, like parts A and B and maybe C, and then a whole host of sort of modifications and applications rather than just a series of different calculations on a single question. Okay, so for part A, we're kind of going right into it, and we just want to know the direction that current flows through this resistor that I'm going to be drawing in here in a second. We have a bar that's moving, and we have a resistor R. I'm going to use capital L rather than the curly L, just it's easier to write. We have a bar that's moving at some velocity v, because we're applying a force to it. And in this whole region, there's, right, this should be all uniformly spaced, but that would be really hard to do, so just kind of take it as granted that it is, and this is out of the page. Okay, so everything's conductive, everything's frictionless, but there is some resistance in it. So the first question is just, what direction does the current flow in the resistor? And that's sort of up to the top of the page or down to the bottom of the page. Those are our two options. And knowing that we have a conducting thing moving in a magnetic field, that should immediately tell you what you're going to be working with, right? And also, it even says in the problem, right, an induced current. So what do we know something about an induced current, and that uses Lenz's law, or that right-hand rule. We don't have to calculate it yet, right? We can calculate an induced EMF. That's going to be part B, but the direction is just given by Lenz's law. And so if you forget how to do that, but you remember that this thing called Lenz's law is relevant, then simply writing down that you're trying to use Lenz's law gets you a point, even if you have no idea what to do with it, right? If you recognize how you indicate the direction of an induced current, what you would use, that's better than nothing. So we're going to use this Lenz's law thing. So as the bar moves, right, it makes the, right, this is sometime later, it makes the area enclosed bigger, right? If it makes the area enclosed bigger, that increases the magnetic flux, right? The magnetic flux is this capital phi thing, which is B times A. So we've increased A, so we've increased phi. So the induced current will want to produce a field that would decrease the magnetic flux, that opposes that change. That means we want to induce, so we want to induce B into the page. And now we just need to use the right-hand rule to figure out what current will induce a magnetic field of that direction. So your thumb points in the direction of the current, and your fingers have to curl in the direction of the magnetic field you want to form. And since we care about the region in here, that means you need to have your fingers curling down or into the page on the inside of that resistor. And so that means your thumb has to point up. And so we have to induce a current up. And right, if you just draw that arrow and label it like that, then that satisfies it. So part A, despite really not doing any math, is quite a tricky one. Everything else I think is actually simpler for once. So part B, now I actually want to calculate something about this, which is first the induced EMF in the rod. Okay, we have an equation for that on the sheet. Actually, I'm going to write it with the, well, actually, yeah, let's leave it as it was. So, right, EMF can be a delta V or that epsilon kind of thing. And this is negative delta phi over delta T, the rate of change of the magnetic flux. And I just wrote what the magnetic flux was, but the magnetic field itself is not changing, just the area. So negative B delta A over delta T. And now we can look at the drawing. We realize that the area is only changing in one way, right? Which is specifically the horizontal, right? If this is like delta X. The area is L delta X as time goes on. And delta T is, right, however long it takes. But this is a velocity. So negative B, oops, I got sloppy with notation. This L is supposed to be that cursive L. Right? And if you forget the negative sign, that's okay. You've already sort of done the direction in part A, so all you need is this expression, B times L times V. Now, you also notice that this expression is actually on the AP sheet right now. If you remember what that was derived from, which is the motional EMF concept, then you can just use it. Right? This is obviously like not a question you're likely to get this year, but you can also show where it comes from if you didn't remember that. All right, in part C, if you got part B, all we're trying to do is relate a potential difference, or an EMF, to an electric field. So the electric field E is an EMF divided by a distance. So I'm going to leave just as D for now. So we need to think about what this distance means. We know the current is flowing, right, like from here to here. Right, that's where our potential difference is across, and that's a length L. So this is BLV over L. Another way to come at it is that since the velocity is constant, the induced EMF must be constant. Therefore, the electric field must be constant as well. And the only length in the problem that isn't changing is L. So it can't be any other value. So that gets you BV. And so that's part C. All right, moving. So part D, we don't know, now we want to figure out the magnitude of the induced current. We have the induced EMF, and we want the current across through a resistor. So delta V equals IR. The potential difference is the EMF. The resistance is R. And I is what we're trying to find. So we just plug that in. And we're done. Once again, a fast step, but recognizing that you can use Ohm's law equally well for induced EMFs as well as sort of chemical battery EMFs. It doesn't change anything, right? So you just kind of plug it in. Power dissipated, right, is next. We have a couple expressions for the power. The easiest one to remember, I think, is that one. That's that one. The AP sheet has, I believe. Of course, as I check that, I realize they don't. This one is a derived result. It comes from combining what the AP sheet does have, which is the power dissipated in a resistor is this, with Ohm's law, right? If you take this and put it right in there, you get that. So if you used I delta V, right, we get BLV over R, right? That's I. And part B told us the potential difference across the resistor, right, which is just BLV, right? So we can combine all that. We get B squared, L squared, V squared over R. Right, so that's the power. Once again, pretty much just a fast substitution, but you have to recognize that all these parts are sort of consistent. Finally, we need the magnitude of the external force that we have to apply to the rod to keep it moving at constant velocity, right? Because part E says power is being dissipated. And if we think energy is conserved, then that means the rod's kinetic energy has to be going into that power dissipation, right? So without an external force, the kinetic energy would leave the rod and it would stop. Right? So what we need is to figure out the force that has to sort of balance that slowing down. And there's two different ways I think you can do that. The first is to use the result from part E directly, which is sort of what I was guiding you to with that explanation. So I'm going to do that one first, then I'm going to show you the other one. So the power you have to supply must equal the power lost in the resistor. So this, right, we can know the calculation of power to make it move at a constant velocity is a force times that velocity. And the power lost is what we found in part E, b squared L squared V squared over R. Right, this says that sort of whatever you put in is immediately lost, so you keep your energy constant or your velocity doesn't change. Right, this is a Physics 1 concept. It's on the equation sheet as well, but the definition of power in terms of the constant force and the constant velocity. And we see that all that really happens if we do that is we just cancel some factors of velocity. And so we get that the force must be b squared L squared V over R. It's a terrible R. So that's one way, right? That gets you the answer, you're done. The other way is to do it in a more Newton's law sense, right? If this is our rod, there's a current flowing through that rod, right? If it's going up through the resistor, it's going down through that, but it's the same current because it doesn't have anywhere else to go. That's a current in a magnetic field, and that feels a force. So we need to apply a force in this direction that balances the magnetic force in the opposite direction. They have to be equal and opposite for it to move at a constant velocity. So F has to equal magnetic force, which equals B times L times I, right? That's another one's on the AP sheet, the definition of the magnetic force on a current carrying wire. And so we just need to rewrite what I is, right, because B and L are things that are already fine. And we already calculated that. That was part D. So this is B L V over R. So that gives us, sure enough, the same thing, B squared L squared V over R. So either one of those approaches will work. I like the power approach a little bit more, but you have to remember a little bit more for that one as well, right? The forces in free body diagrams should be a more familiar concept. So once again, this is a question that is not a perfect analog to things you're likely to see, but I wanted to use it as a review of how all these terms are related and how you can put them all together.